Welcome back to another explainer. Today, we're putting on our lab coats and stepping right into the laboratory to solve a pretty fascinating everyday chemical mystery. Guided by the procedures of Dr. Chem, we're going to figure out exactly how to determine the precise acid content in something that's probably sitting in your pantry right now, vinegar. Okay, let's dive into this with a super practical problem. Imagine you've got a bottle of dark, rich, totally turbid balsamic vinegar, and you need to know its exact acidic strength. Now, traditionally, chemists use a chemical indicator that magically changes color to tell them when an acid is neutralized. But here's the catch. If your liquid is already pitch black or just incredibly cloudy, how can you possibly see a delicate little pink color change? Well, the short answer is you can't. So that brings us to a choice between two totally distinct analytical methods. First, we've got traditional volumetric titration. This relies heavily on visual color indicators, which, as we just established, completely fail us in turbid or highly colored solutions. But on the flip side, we have conductometric titration. Instead of looking for a visual color change, this method relies on tracking electricity, electrical conductance, to be exact. It's absolutely perfect for colored solutions, very dilute solutions, or even systems that involve relatively incomplete reactions, like the neutralization titration of phenol, which traditional indicators simply can't handle. Section 1. Enter conductometry, the invisible dance of ions. So, by definition, conductometric titration is an electroanalytical method. Basically, during the titration, one ion in the solution is replaced by another. And because these ions have different conductivities, the overall electrical conductivity of the whole solution actually changes as the reaction progresses. By plotting this change in conductance as a function of the volume of the titrant added, we can precisely locate the equivalence point. We aren't looking for a visual cue here. Instead, we're carefully listening to the electrical capacity of the solution as the ions swap places. It's brilliant. To make this abstract concept a bit more visual, think of it like a relay race. Imagine incredibly fast runners. These are our hydrogen ions, or H+. As the titration happens, they pass the baton to much slower runners, the sodium ions, or Na+. Because the slower runners take over, the overall speed, or in our case, the electrical conductance, literally drops. It's this measurable difference in mobility that makes the whole technique work. So the crucial point is that setting up a flawless titration requires strict adherence to Dr. Chem's golden rules. First, throughout a titration, the volume of the solution is always increasing, which can cause nonlinear curves unless you correct for it. To avoid this and keep the volume change small, your added reagent, the titrant, must be 10 to 20 times more concentrated than the solution being titrated. Furthermore, for maximum accuracy, the angle between the two branches of your titration curve should be as acute or sharp as possible. And finally, the added reagent should be a strong electrolyte to ensure a clear, really measurable impact on the conductivity. Section 2. Dr. Chem's vinegar experiment. All right, let's step directly into Dr. Chem's shoes and run through the precise chronological steps of the lab setup. First up, we must calibrate our conductometer, typically using a standard 0.1 molar potassium chloride or KCl solution. Once calibrated, we carefully pipette 30 milliliters of our diluted vinegar solution into a beaker. Next, we fill a burette with our strong base, which is 0.1 normal sodium hydroxide, or NaOH. We then add this base in small, highly precise 0.5 milliliter increments, and after every single addition, we stir the solution well and record the new conductance value. And this brilliantly illustrates the setup in practice, which requires absolute precision. Notice the burette suspended right over the beaker containing our vinegar sample. The conductivity cell dips directly into the solution, connected to the conductometers. There's also a magnetic stirrer at the bottom to ensure really thorough mixing after every 0.5 milliliter addition of our strong base. Oh, and one absolutely vital precaution noted in the lab manual. The platinum electrodes must be completely immersed, and you must ensure absolutely no air bubbles are trapped between them. If they are, it'll completely distort the electrical reading. Now, what's really interesting about this slide is what happens when you plot the conductance against the volume of sodium hydroxide added. You get this distinct, slightly curved V-shape. This is the classic curve of a weak acid, like the acetic acid in our vinegar, being titrated with a strong base. Initially, the conductance is quite low due to the feeble ionization of the weak acetic acid. Actually, you'll even notice a slight initial dip. This happens because the newly formed acetate suppresses the remaining acetic acid from breaking apart, a phenomenon known as the common ion effect. But then, we hit a turning point. As more NaOH is added, it neutralizes the undissociated acetic acid and converts it into sodium acetate. Now, sodium acetate is a strong electrolyte, meaning it's highly ionized. Consequently, the conductance begins to rise sharply. This increase continues right up to the equivalence point, the exact moment of complete neutralization. Beyond that point, the conductance shoots up even more rapidly. Why? Well, because we're now introducing an excess of highly conductive, really fast-moving hydroxide ions, or OH-, straight into the solution. Section 3. Catching adulterated vinegar. Let's imagine a scenario where a fraudster tries to cheat by spiking cheap vinegar with a strong acid, like hydrochloric acid, just to artificially boost its sourness. If we were using standard visual indicators in a dark liquid, we might literally never know. So what happens to our electrical conductance curve if the vinegar is secretly carrying a payload of strong HCl? Let's move to and see how this builds when we actually compare the data. Looking at a pure weak acid curve compared to a mixture of a strong and weak acid, notice the drastic difference. Instead of a gentle dip and rise, we get a steep drop followed by a rise, resulting in a telltale double break point. Here are the mechanics behind that double break reveal. In the spiked mixture, the initial conductivity is very high because of the strong hydrochloric acid. The HCl completely suppresses the ionization of the weaker acetic acid. As we add our sodium hydroxide base, the extremely fast hydrogen ions, which have a mobility of 350, are swapped out for much slower sodium ions, which only have a mobility of 43. This causes a sharp, immediate decrease in conductivity. This sharp drop continues until all the strong HCl is neutralized. Only then, at that first break point, does the weak acetic acid finally begin to ionize and react, causing the conductance to rise towards the second breakpoint. The graph literally draws us a map of the fraud. This brings us to a really powerful realization, summarized in our source material. Quote, "The electrical conductance of a solution is a measure of its current carrying capacity. It is a non-specific property. By itself, a raw conductance reading doesn't tell you what is in the solution, just how well it carries a current. But, as the source concludes, conductometric titrations, in which the species in the solution are converted to non-ionic form by neutralization, are of more value. By systematically tracking that non-specific property during a chemical reaction, we transform it into a highly precise, revealing analytical tool." Which leaves us with this final thought to ponder. If tracking the simple, invisible dance of ions can effortlessly bypass dark, turbid liquids to accurately map acidity and catch fraudulent spiked vinegar in the lab, what other hidden chemical truths might this method reveal in the everyday liquids you consume?